Hi, this is Mr. Beck. This is lecture 3 in my magnetism series, which really should have been my electromagnetism series, but that ship has sailed. So let's continue. In this lecture on electromagnetism, we're going to cover a couple things. First, we're going to review the right-hand rules 1 and 2 because we're going to be using those in this lecture. Number 2, we're going to talk about crossed electric and magnetic fields, a way to use both the electric field and the magnetic field and have both of them affecting a charge at the same time. We're going to talk about the force on a current carrying wire that is in a magnetic field. So a wire will have a current in it and it's going to be placed in an external field. We're going to see what happens with that. We're going to talk about the force between two parallel current carrying wires. So when you have two wires that both have a current, one of them is going to be generating a field, the other one's going to be generating a field, and those two wires are going to interact. So key topics for today. So first, let's review the right-hand rules. Remember, the first right-hand rule had to do with the current in a current carrying wire. So the wire has a current, in this case, the current's running to the right. And the first right-hand rule says that if we line up the thumb of our right hand in the direction of the current, what happens is that a magnetic field will be created in that wire, and the direction of the magnetic field are going to be the direction that the fingers would wrap if you grabbed onto the wire. So this is thumb sticking out and you grab on top of the wire, that means that on this wire with the current running to the right, the magnetic field would come across the top, down in front, down underneath and back. It'd be going away from you, and behind the wire it'd be going up to the top. So that is identifying the direction of the magnetic field around a current carrying wire. Our second right-hand rule had to do with setting our three fingers 90 degrees apart from each other to identify the direction of the force on the moving charge. So if we have the middle finger representing the magnetic field, M for middle, M for magnetic, and we have the index finger, letter I for current, and I for index finger, and that would be the direction of either a positive charge moving or the current in a wire. Then our thumb is going to be the direction that the wire is going to be feeling a force, as in hitchhiking, hey, I want to go that way. So the thumb is the direction of the force on a positive charge. Now those are our two right-hand rules. Now let's look at crossed electric and magnetic fields. What happens when we have a charge that could be subject to both? So we'll start with a positive charge entering the region of a constant external magnetic field. So we've set up some magnetic field B, and we're going to have a charge flying in at a velocity moving to the right. Now what happens is when that charge enters the field, that charge is going to feel a force, and if we use the right-hand rule, we have the right-hand rule, it's a positive charge, the charge is moving to the right. The magnetic field, the B field, that's dots, and dots are coming towards you, what that means is that the force on the charge would be in the downwards direction. So I have a charge moving to the right, the force is in a downwards direction, and if that charge keeps on moving, it's going to move in a circular path because that force is going to wind up being a centripetal force. The force will always be perpendicular to the direction of the velocity, so that would make it move around in a circular path. Now, if we didn't want it to move in a circular path, how could we have that charge move in a straight line instead of the circular path? Well, we know that an electric field also will affect a charge. So if we set up a magnetic field, what I'm doing is putting positive charges on the bottom and negative charges on the top. So I'll get an electric field that points straight up from the positive plate to the negative plate. Remember, the electric field points in the direction that a positive charge would feel a force. So the electric field is pointing straight up. And since that is a positive charge, the positive charge will feel a force from the electric field in the upwards direction in this situation. So now I have an electric force pointing up and a magnetic force pointing down. If I can have the magnitudes of those two forces equal to each other, then forces would be balanced and the charge would continue in a straight line. So this is a way to have the charge travel through a magnetic field and an electric field at the same time and maintain a straight path. Now we call these crossed electric and magnetic fields because in this case the magnetic field is coming straight towards us and the electric field is going straight up. So that means that they are actually 90 degrees from one another and also 90 degrees from the velocity of the charge. So the charge is moving in the plane of the page to the right, the electric field is in the plane of the page straight up, and the magnetic field is perpendicular to the plane of the page, so perpendicular to the other two, perpendicular to the velocity and the electric force, and the electric field. So if the electric field and the magnetic field both create forces on the charge and those forces balance, then the charge will move in a straight line. So what does it mean when the electric force and the magnetic force are equal? Well, the electric force on a point charge is going to be the amount of charge times the electric field, or Fe equals Q times E. The magnetic field, of course, the magnetic force we learned is QVB, the amount of the charge times the velocity times the magnetic field strength, QVB. So I have QE equals QVB. Now you'll notice there's Q on both sides, so the charge will cancel out. So it doesn't matter what the magnitude of the charge is. All that matters is the relationship between the electric field, the magnetic field, and the velocity. So if we rearrange that equation, E equals VB, we rearrange it and solve for velocity, we get the velocity is going to equal the strength of the electric field divided by the strength of the magnetic field. So V equals E over B. What this means is once I set up a certain magnetic field and a certain electric field, then particles of a very specific velocity, the velocity being the ratio of E to B, E divided by B, any particle with that velocity will travel straight through the field. And it doesn't matter what the charge of that charge is or what the mass of that charge is. So heavy charges or light charges or positive charges of large magnitude, even negative charges. Let's take a negative charge for a second and put it here. If you had a negative charge that was moving to the right in this field, then it would feel an electric force opposite the direction of the electric field. So the force on a negative charge would have electric force pointing down. And then if we use the left-hand rule, we would see that with the magnetic field, so I'm using my left hand now, a magnetic field pointing towards you and the charge moving to the right, that would yield a force in the upwards direction. So what we get is a magnetic force pointing up. So my FB would be in the upwards direction. So still, that any charge with the same velocity is going to have move unobstructed through that magnetic and electric field. So this is interesting with the crossed electric and magnetic fields. We have it's a velocity selector. It'll pick only charges of a particular velocity. Our next topic is a current carrying wire in a magnetic field. We're going to have so many different examples of wires and loops and charges moving and creating fields and such, so it does get a little confusing to put it all together, but this is our next example, a current carrying wire in a magnetic field. So I have a magnetic field B and I have a current I in a wire that is in the plane of the page. The magnetic field is X's, so that's pointing directly into the page. Now, if I have that current carrying wire, it turns out that that wire has many charges that are moving. Actually, we now know that it's negative charges moving to the left and not positive charges moving to the right, but we have the convention of a positive current being the direction that positive charges would move if it were the positive charges that were moving. So let's just imagine for a second that the positive charges are moving with certain velocity to the right. Each one of those charges is moving in a magnetic field and is going to feel a force, but that force is not going to change their direction because the charges are trapped within the wire. So the charges are still going to be moving to the right, but each one of them is going to be feeling a magnetic force, in this case, in the upwards direction, because with the right-hand rule, my right hand again, I'm going to take my velocity and point to the right. The magnetic field is pointing away from you into the page. That would mean that the force is going to be in the upwards direction. So each one of these little imaginary charges is feeling a magnetic force in the upwards direction due to the right-hand rule. Now, what the cumulative effect of those forces on all of the moving charges is going to be that there's a net force on the wire in that same direction. So again, the right-hand rule is going to still apply, where we can apply it to the entire wire as a whole, as opposed to just individual charges. So the entire wire will feel a net force, and if you apply the right-hand rule and you line your index finger up with the current pointing to the right, and you have the magnetic field pointing into the page, then your thumb is going to be pointing in the upwards direction. So this is index finger for current to the right. The middle finger magnetic pointing into the page would give you a force in the upwards direction. So the right-hand rule still applies. The magnitude of the force is given by the equation BIL sine theta, where B is the magnetic field strength, I is the current in the wire, L is going to be the length of the wire that's within the magnetic field. So it might not be the entire length of the wire, but it's going to be the length of the wire that is enclosed within that ideal magnetic field that we've drawn here. And then we have sine theta. Well, theta is going to be the angle between the magnetic field and the current. So if the current here is moving to the right and the magnetic field is going into the page, what that tells me is that those two are at a 90-degree angle. So sometimes we're going to leave off the sine theta if it's perpendicular, because the sine of 90, of course, is 1. And so if the magnetic field and the current are perpendicular to one another, we'll get the full force. However, if the wire were pointing straight into the page or straight out of the page, then what we're going to see is that theta is going to be 0, and there's going to be no force on that wire. So if the wire is pointing in the same direction as the magnetic field, then there's no force on that wire. So let's take a look at an example. Let's say that we have a situation where you have a 0.3 meter length of wire with a current of 1.5 amperes flowing through it, and it's perpendicular to the magnetic field of 0.6 Tesla. Well, in this case, we have our equation that the force magnetic is BIL sine theta. If we substitute the values, we substitute 0.6 Tesla for the magnetic field strength, 1.5 amps for the current I, 0.3 meters for the length of the wire, and then since it's perpendicular, we're going to put in sine 90, which of course is 1. Do those calculations, and we get a value of 0.27 newtons as the force on the wire. Now we have the situation where we have parallel current carrying wires. This is an interesting situation because we don't have something else generating a magnetic field. But you know that a wire with a current running through it is going to generate a magnetic field of its own. And these two wires are going to interact with a magnetic force between them because of the magnetic fields that each one of them generates. So let's step through this one step at a time. So I have a top wire with current I1, and I've drawn that in blue. I've got the bottom wire with current I2. The wires are parallel to each other. I'm interested in a certain length of that wire, L, and the wires are separated by a distance R. Now the first thing that happens is that the first wire, wire 1, is going to generate a magnetic field near wire 2. It's actually going to generate a magnetic field, throughout all of space, but I'm interested in what's happening near wire 2. And if we use the right-hand rule, what we see is that with the current moving to the right, my right hand would wrap around the wire this way. That means on the top of the wire, the magnetic field is coming towards me, and on the bottom of the wire, the magnetic field is going away. So the magnetic field is going to form X's below the wire, below wire 1. So I have X's below wire 1 in the region of wire 2. So wire 1 generates a magnetic field near wire 2. Now I have the situation, so the magnetic field near the current carrying wire, we could use the equation that the magnetic field due to wire 1, so B1, is going to equal mu naught over 2 pi I1 over R, because it is wire 1 that's generating that magnetic field. All right, now we have a wire 2 that's going to feel a force because it is a current carrying wire within a magnetic field. Now, if we take a look again at the right-hand rule, what we've got is a current moving to the right, a magnetic field pointing away from you into the page, and that would result in a force in the upwards direction. So wire 2 is going to feel force in the upwards direction towards wire 1. And the force on that wire, the force on wire 2, is going to be the magnetic field strength generated by wire 1 times the current in wire 2 times the length of the wire times sine theta. And theta, again, is between the wire and the magnetic field. Those are perpendicular in this case. So F2 is B1 I2 times L sine theta. Now, you notice that I have B1 defined up here. What I can do is substitute that in where I have B1 down here. And what that gives me is that the force on wire 2 is going to be mu naught over 2 pi I1 over R times I2 times L sine theta. And I can summarize those over here, multiply that I2 up on top. So now I have the force on wire 2 is mu naught over 2 pi I1 I2 over R times L sine theta. And that is the magnitude of the force on the bottom wire pointing up towards the top wire. So that's our first step, is what's happening to the bottom wire. Our next step is going to be, well, what's happening to the top wire? Let's take a look at the top wire. Now I've got the top wire and I've got a current in the bottom wire. So the current in wire 2 is going to generate a magnetic field near wire 1. So just like we did before, we have a right-hand rule for wire 2. The current is going to the right. Therefore, the magnetic field is going to be towards you on the top of the wire and away from you on the bottom of the wire. So if we take a look at that, it's generating this magnetic field towards you on the top of wire 2 and away from you on the bottom of wire 2. The magnitude of that field is going to be B2 is mu naught over 2 pi I2 over R, because it's current 2 that's generating magnetic field 2. Now I've got the current carrying wire I1 that's sitting in the magnetic field of wire generated by wire 2. So if I take that, wire 1 is going to feel a force because it now is a wire that's carrying current and it's sitting in a magnetic field. In order to figure out this direction of the force, again, I have right-hand rule. The current is going to the right. This time, the magnetic field is pointing towards you, which would result in a force on that wire in the downwards direction. So wire 1 is going to feel a force in the downwards direction. The magnitude of that force on a current carrying wire is BIL sine theta. Now it's the force on wire 1 is going to equal the magnetic field from wire 2. That's the external magnetic field that wire 1 is feeling, times the current 1 times L sine theta. So F1 is B2 I1 L sine theta. Now again, I can substitute this B2 whole term in where I have B2. And what I get is that F1 is mu naught over 2 pi I2 over R. That was my substitution of B2 times I1 times L sine theta. Now again, if I bring I1 up into the denominator where it belongs, I get that the force on wire 1 is equal to mu naught over 2 pi I1 I2 over R times L sine theta. Now you should notice something here. It turns out that the force 2 is the same as force 1. So we've gone through these whole steps, and now I have the force on wire 2 is exactly the same magnitude as the force on wire 1. And you'll notice that they are in opposite direction. So it is the same magnitude force, and it's an equal magnitude in opposite directions. Now that should ring a bell to you. When you have equal and opposite, that should remind you of Newton's third law. We should have expected that the force on both of the wires is going to be the same because of Newton's third law. But this even is the case if I1 and I2 are not the same as each other. Think about it. If I1 was very large, then it's going to be generating a very large field near I2. So I2 will feel a strong force because of the large field generated by I1, even if I2 is small. Now I2 will generate a weaker field near I1, but that weaker field times the stronger current will again lead to a strong magnitude force. So since they're related, and since you can see that the equations are basically the same, what we get is that the forces are always going to be the same between the two wires, even though you could have different magnitudes of current. But this is obviously the case because if wire 1 is exerting a magnetic force on wire 2, then wire 2 must exert an equal and opposite magnetic force on wire 1 because of Newton's third law. And so if I have the currents going in the same direction, this is what I've done in this case, is I've shown them in the same direction. I've shown that the wires will attract one another if I have two current-carrying parallel wires with the current going in the same direction. But what happens if the current is going in the opposite direction? Well, let's take a look at current going in the opposite direction. Now I've got current 1 going to the right, and I've got current 2 going to the left. So let's think this through. Still, current 1 will generate a magnetic field using the right-hand rule towards you on the top, away from you on the bottom. So it is into the page in the region of wire 2. So now wire 2 is going to feel a force because it's sitting in that field. Now, you take a second and use your right hand and figure out what direction that force would be. So first, index finger is the direction of the current. In this case, I've got a current going to the left. The magnetic field is pointing away from me, so that would be in that direction. and that would leave the force being in the downwards direction. So a little awkward on the page, but now you see that the force on wire 2 is going to be in the downwards direction. Now, at the same time, wire 2 is generating a magnetic field. So what's that going to look like? Again, right-hand rule. Got your right hand? Point your right hand and put your thumb in the direction of the current. Now, if you wrap your hand around the wire, you'll see that on the top of the wire, it's going away from you, and the bottom wire would be coming back towards you. And that is if the current is running to the left. So let's draw that green field. So the wire is generating a magnetic field towards you underneath the wire and away from you up on top of the wire. So now current 1 is sitting in the magnetic field of current 2. Again, we have right-hand rule. So we have a current moving to the right. We have a magnetic field that's pointing away from you, and that would mean that the force on that wire is going to be in the upwards direction. So we see that it generates a force in the upwards direction. So if the current is in the opposite direction, what we can see is that, of course, the wires are going to repel. So that took a lot of right-hand rules. That's why we reviewed the first and the second right-hand rule before going into the situation. And of course, you can calculate the magnetic field using our equations for the amount of the magnetic field generated near a current-carrying wire, and then the second equation for the force on a current-carrying wire in a magnetic field. And once you've calculated one force, you know the magnitude of the other force as well, due to Newton's third law and due to the fact that the equations turn out to be the same. So, hope that was useful, and keep an eye out for lecture number 4.